So as always, making sure to record myself going through these notes tonight. So if you ever want to go back and rewatch them and watch me going through them once again, you can find them in our Zoom class videos section of the website under Immune System. Or if you scroll all the way down to week 7, yes, you heard that right, week 7 out of 8 this term, we have our Tuesday assignment, or our Tuesday notes, excuse me, on part 1 of the immune system. So if you remember from back in our circulatory system days, you might recognize all of these red guys around here. These are our red blood cells that carry our oxygen. But this guy right here is our white blood cell, which is sort of one of the major components of the immune system. So we'll be talking a whole lot about white blood cells here tonight. So what is the immune system? It's not some sort of big structure that you can point to, like the bones of the skeletal system or the stomach and the intestines of the digestive system. Instead, it's a lot of smaller structures that make up our body's defense. So our bodies are constantly under attack from outside material, whether that's organisms like bacteria or parasites, malfunctioning cells within our bodies like cancer cells, or foreign particles like viruses or allergens. There is a constant flow of these coming in and out of your body, and it is the immune system's job to recognize them and get rid of them before they cause major problems for the rest of our body. So the immune system is all about preventing stuff that gets into our body from doing any long-term damage or having any negative impacts. So these are like the soldiers of your body. The immune system is our armed forces protecting the borders of our body from attack from the outside world. So there are a couple different layers or lines of defenses in our immune system. The first line of defense is different structures that kind of make up the initial contact between you and the outside world. One of the big ones of this is our skin, right? So when you look down at your arm, you don't just see bare blood vessels running up and down over exposed muscle and bone, right? You have this kind of whitish, brownish, stretchy, pliable material called skin. So our skin, specifically the outer layer, known as the epidermis, forms kind of a shield between you and the outside world. So not only does it prevent stuff from having too readily accessible areas to your blood and organs, it also can secrete certain chemicals that help to reduce the number of bacteria and parasites and viruses on the outer portion of your body, because these are in contact with the air 100% of the time, unless you're like swimming and they're in contact with the water. But you know what I mean. So your skin is sort of the initial barrier between your inner bits and the outside world. So skin cells are very easily replaceable. They're essentially, by the time they're on the top of your skin, they're mostly dead. And so you shed between 40 to 50,000 skin cells in an average day. So a lot of the dust that you see floating in your home or gathering on unused TVs or cabinets or whatever, a lot of that dust is made up of skin cells. So you're welcome for that beautiful mental image next time you're cleaning your house. Another important layer that we talked about a little bit when we went over the respiratory system is things in your nose, such as mucus and cilia. So as you're breathing in and out, you have the cilia, which is like tiny little hairs, and the mucus, which is this kind of sticky substance that help to trap foreign particles like bacteria and viruses that otherwise would make it down into your lungs. So you breathe these particles in, they're kind of swirling around in the air, and as they're swirling around, a bunch of them are going to get stuck in the mucus. So not only is there's mucus in your nose, but there's also a little bit of the mucus lining in your throat, in your trachea as well. So after they get stuck in the mucus, we don't want them to just sit in our nose. So the respiratory system will kind of help to sweep the mucus along with these little cilia. So these cilia are like these tiny little hairs inside your nose and kind of along the back of your sinuses. And so they're what's sweeping all this mucus away so that it ends up in your throat. Now, once all of these foreign gross particle things are in your throat, a couple things can happen. You can cough them back out again. So that's sometimes what happens, like when people get diseases where they're coughing a lot, that's because your body is trying to get rid of all these gross extra particles. Or you can swallow them, which sounds gross, but remember, if you swallow your mucus, it's not going down into your lungs to cause all sorts of havoc. It's going down your esophagus instead into your digestive system. And in a little bit, we'll talk about how that stomach acid, that's an important part of your digestive system, helps to break down a lot of that gross mucus and bacteria. Another one that comes instinctively to a lot of people, but that you might not think of, is saliva. So if you're going and you're chopping up some vegetables, right, and oh crap, you nicked your finger. Well, before you get to the sink or get a Band-Aid on it, what's the first thing that a lot of people do? You stick it right in your mouth to not only help there prevent getting blood like all over your clothes and your counter, but also doing this actually helps with the healing process and helps to prevent bacteria getting into your bloodstream. So your saliva actually does contain a lot of chemicals that help to break down bacteria that could potentially infect the cut on your finger. So again, we have our skin on the outside of our body. That's like our shield against the world. But there's a ton of bacteria that are just kind of hanging out on the surface of your skin. They're not really doing anything yet because they're not inside your body. But when you get a cut on your hand or your finger, now they've got an opening and they can swarm in. So the saliva has some chemicals in it that can help break down certain types of bacteria. It's not 100% foolproof, obviously, right? You can't just put a whole bunch of spit on your finger and call it a day, because there are millions of different bacteria out there, and a lot of them don't really get impacted by the saliva, right? Your saliva is not Clorox, right? It's not going to break down 99.99% of disease-causing bacteria. It'll get some of them, but not all of them. And then finally, one of the final parts of your first line of defense is your stomach acid. So earlier I was talking about how the mucus that gets into your throat, you can swallow it and it'll go down into your stomach. That's because your stomach is an extremely toxic environment for a lot of these bacteria. We mentioned that your stomach has these really strong acids in it, that break down your food. Well, while they're breaking down their food, they can also destroy a lot of bacteria. So I mentioned when we were going through the digestive system that your stomach has its own special mucus to help prevent it digesting itself. Otherwise, it would be destroying its own cells also in the process. So it is protected from its own juices, but these juices, these stomach acids, are strong enough to where they can kill a lot of the bacteria that might try to enter your body through your digestive system. So one kind of important thing to note about your digestive system is that the stuff that is inside of your digestive system, inside your stomach and your intestines and stuff, it's inside your body, but it's not really inside your body. Confusing, I know, but here is what I mean by that. So if you think of your body and your digestive system like a tube, right? You have an opening on one end, and that's your mouth, and you have an opening on the other end, and that's your anus, and the food passes through this tube and gets broken down along the way, right? So the food is digested inside the tube, but it never really enters the plastic, the actual makeup of the tube itself, right? The plastic part of it. Eventually, yes, when all of those nutrients and stuff get broken down, they go into our body cells and stuff, right? But the food and the waste product doesn't. So that's what we mean by inside, but not inside. Sure, it may be within kind of the confines of your actual body, but the stuff going through your digestive system isn't directly interacting with your cells or your tissues or your bones or anything like that. It's just being passed through a tube. So that's why if bacteria or viruses get into your digestive system, they get dissolved by that stomach acid without actually entering your body cells and causing damage. They're going through the tube. They do not get absorbed into the plastic part, right? They go through your digestive system, but they don't get absorbed into your cells and your body. They get broken down by that stomach acid before they get there. All right, so any questions on sort of like these first line of defense options, or what we mean by talking about a tube within a tube? Oh, hi, Ms. Clarkson.
Hello, Mr. Stanley. This is cool.
Yeah, immune system is wild stuff.
Yeah, I was gonna ask, I was like, this is the immune system?
Mm-hmm.
Wow. I was going gastro, but no, okay. Very nice, very nice. Checking out and see how you guys were doing. I'm just doing a drive-by, and
Cool.
I just wanted to see. But yeah, this is super interesting. I'm all like, really? Okay. All right. Okay. I wish I could stay. I have to go to and bother more people, but thank you for letting me hang out a little bit.
Yeah, no problem. Anytime.
Okay. I'll come back and see you guys. Bye.
Okay, sounds good.
Bye. Bye.
All right. For those of you that don't know that lady, that's Nicole Clarkson. She's the campus director for the Norwood Night School. She's a really awesome lady. If you ever get the chance to meet her, would highly recommend. She's technically my boss, but we all like her a lot. She's really great. All right. All right, so here we go. So just to kind of reiterate, the outside or the inside surface of the tube is your digestive system. The outside surface of your tube is like the skin, but then that plastic ring that's circling the tube, that's separating the inside from the outside, that's like the rest of your body, your cells, your tissues, your organs, your muscles, your bones. That's what all that is representing. So you may have heard about gut fauna before, which is bacteria that live in your gut, in your stomach, which is confusing because one of those bacteria, Escherichia coli, aka E. coli, some of the strains of E. coli are really damaging to humans if they get into your body, into your other organ systems. But you find tons of E. coli in our digestive tracts. So why aren't we sick all the time? Why aren't we constantly getting infected by E. coli?
It's good bacteria.
And not only is it good bacteria, but it's hanging out in our digestive system, which, like we said, is not fully it's not inside our other body cells. So the bacteria are technically not inside our body. They're inside the digestive tube, which keeps them separate from the other cells of our body. So only if we get infected through the skin or there's some sort of ulcer or cut in our digestive system that they're able to break through and get into our body cells that way, that is when they bypass that first line of defense and can start doing some damage. So they and their other millions of brothers and sisters can hang out in our digestive system just fine and are actually extremely useful in helping us break down some of our food. But it's if they cross that barrier and get into our actual body cells that they start causing problems.
Probiotics.
Yep, exactly. That's why the big deal these days is the probiotics, trying to keep those gut bacteria happy and healthy. So let's say something not ideal happens. You get a cut on your hand or leg, and some bacteria or viruses are able to infiltrate your body and bypass that first line of defense. Luckily, we have our second line of defense. So our stuff inside of our body cells and bloodstream that helps fight off infections that make it to that point. So our white blood cells are a major component of this second line of defense. So if these invaders actually get inside the body, then the white blood cells, which are going to come up a lot, so I'm going to abbreviate them as WBCs in terms, I'll probably still say white blood cell, but there'll be WBCs in the text on the slides. So white blood cells are what will attack these foreign invaders. So normally they're just kind of passively circling around our circulatory system, making sure that everything is cool. But if an infection starts happening in, say, a certain section of skin cells or muscle cells, then our white blood cells can actually get into those tissue cells and start working to drive out the invaders. So these guys are going to head to wherever there's a problem and try to get rid of the infection at its source. So one type of white blood cell that's really cool is called a phagocyte. So phagos or phagos is a Latin word meaning essentially like eat. Like if you think of the word engulf, that's kind of similar. So phagocytes essentially eat the bacteria or virus cells. So the phagocyte will kind of envelop the bacteria. So you see here, it's kind of stretching out these guys to circle around the bacteria and then absorb it into the phagocyte itself, where little structures called lysosomes will break down that bacteria or that virus or that parasite, whatever type of foreign particle is there. So that's one way our body gets rid of infections. These cool white blood cells, these phagocytes, literally go around engulfing and eating these foreign particles. Now, they're not technically eating them because they're not breaking them down for energy or anything like that. But they are there. They are breaking them down and breaking them into all their little individual pieces in these lysosomes. So they sort of attack, surround, and kind of engulf these particles. So bacteria like the E. coli that we were just talking about is one type of invader. And bacteria are just little tiny cells that infect our bodies and try to use our bodies to grow and reproduce. Viruses act a little bit differently than bacteria. They also use our body to grow, but instead of just sort of hanging out and growing in certain areas, instead viruses try to go inside of our cells. So like obviously a major virus in the news right now is the coronavirus, naturally. And so just like all other viruses, the coronavirus works by infiltrating one of the cells of your body, hijacking that cell so that it becomes a virus-making factory. So instead of being a nice, normal, happy cell that's doing its little cell job, instead, the virus uses that cell to create more and more and more and more copies of itself. Eventually, there'll be so many virus particles that the cell will burst open, and now thousands of virus particles are spreading throughout your body, going on to infect thousands more cells, or they'll make even more thousands of virus particles. So this is how viruses spread throughout your body. Instead of just trying to grow on their own, they grow by taking over your own host body cells. One of the other cool second lines of defenses that our bodies have against specifically viruses is a chemical called interferon. So here is a pretty typical virus structure right here. This guy is a virus known as a bacteriophage because he normally infects bacteria cells. The coronavirus looks a little bit different. It's more of like a circle with lots of little things sticking out of it. And so when viruses are infecting cells and making all these thousands of copies of themselves, that doesn't go totally unnoticed. Instead, if your body cells start getting infected with virus, they'll release this chemical called interferon, which is a chemical that, get this, interferes with viruses and their ability to attack and infect other body cells. So essentially, it's a chemical that makes it harder for viruses. Once they infect one cell, it gets harder for them to infect more cells down the line. Now, obviously, this doesn't completely stop the virus. Otherwise, we would never have problems with viruses. They'd infect one cell and have it be done. But it is one way that our body tries to slow down the virus invasion a little bit by producing these chemicals that interfere with viruses. All right, so what if you start getting a whole bunch of body cells that get infected? They're being taken over by these viruses, and your body has to try and put a stop to it. One of the major cells, types of white blood cell that helps to fight infected body cells, are called T cells. So T cells are sometimes called helper Ts or killer Ts. And they're responsible for recognizing essentially abnormal human cells. So one of the major things that the immune system has to do, that we'll talk about a couple slides from now, is recognize what is a person cell and what is not a person cell. Or even more specifically, what is a U cell and what is not a U cell. So T cells are one of the ways that our immune system recognizes and destroys human cells that have been infected. All right, so those phagocytes that we were talking about earlier, and a lot of the white blood cells are focused on recognizing foreign cells that got in, so not human cells, not Mr. Stanley cells, and attacking them there. T cells keep an eye on the human cells and have ways of determining if they're infected, and if they are infected, they'll attack and kill the infected cells. So they also are helpful for recognizing cancer cells, because cancer cells are also human cells that are not behaving correctly. They're growing out of control and creating these tumors. So T cells are also used in order to recognize and destroy cancer cells as well. So they're able to recognize these cells, attack and kill these cells, sometimes in great numbers, and then continue on and look for more infected cells to try to take down. Any questions on some of our different white blood cells so far, or some of the different aspects of sort of the second line of immune system defense?
Quick question.
Mm-hmm.
I heard someone say that viruses aren't actually alive. How does that work?
So that is an excellent question. And that is something that kind of science is still trying to classify. So there are a couple different characteristics that are required for things to be considered living, right? So there's things like it has to break down cells for energy, or it has to break down chemicals for energy. It has to be able to make more copies of itself and reproduce. And there are a couple other ones. It has to be able to respond to outside stimuli, either light or heat or different chemicals, stuff like that. So that's what separates living things like plants and animals from things like minerals and rocks, right? Viruses are a sort of gray in-between area, because viruses do not produce or do not break down material for energy, right? They don't produce any energy at all. And they also cannot replicate on their own, right? They don't have any, if you put a whole bunch of viruses together in a petri dish and stuck it in ideal conditions, you cannot get more viruses, because they can only reproduce by infecting other cells. So, so they don't use energy. They're literally, so a virus is essentially just a little bundle of DNA or RNA, which are types of nucleotides that we talked about way back when we went over the macromolecules, wrapped up in this protein coat. And then they just sort of float through the air, through the water, through the bodies of living things. And so if they come into contact with living cells, then they have just enough different abilities to be able to get into those cells and to start combining their own RNA or DNA with the host cell DNA and sort of hijacking the DNA process to create more virus cells.
Okay.
But since they can't do that on their own, they have to infect the cells of other organisms in order to create more copies of themselves. They're not technically considered alive.
Cool. Thanks. I didn't mean to get you off topic. I was just really curious about that.
No, that is an excellent question. And you could ask any biologist, are viruses alive? And I'm sure they'll have very long and lengthy answers to go into.
They're kind of their own thing.
Yes, exactly. They're kind of their own thing. They're sort of living, but also not really.
Sounds kind of parasitic and almost like a spore at the same time.
Yeah, exactly. It's basically that, but on a
Microscopic.
tinier and much more kind of scaled down level.
Cool. Thank you.
So one of the kind of side effects of these T cells and these white blood cells rushing to an area in order to attack infections is inflammation. So when body cells get injured, they release chemicals called histamines. And those are sort of, the histamines trigger a whole bunch of stuff to happen in that area. So when an infection happens, our body wants the white blood cells to be able to get there as soon as possible. So remember, I was saying earlier, white blood cells normally just sort of float around in your bloodstream, and they travel in your bloodstream in order to get to areas of infection. So in order to get a lot of blood flowing across an area so we can get a lot of white blood cells there quickly, we have this inflammatory response. So the capillaries dilate, so those little tiny blood tubes get a little bit bigger, so more blood can flow through them. There's chemicals called pyrogens that get released, which are hormones, and they cause the temperature in not only that area, but in your body to start rising, because a lot of bacteria and viruses can't operate above a certain temperature. And we get white blood cells that flood into the infected area, which is what causes that sort of puffiness and tenderness, because now instead of blood flowing normally through that area, you've got a whole big clump of white blood cells and phagocytes and T cells all converging on that infection area. So whenever things start to swell up, that swelling is due to the white blood cells being prevalent in much higher numbers than they normally would be. So all that is due to histamines, which are also involved in allergic reactions, which we will talk about. I can't remember if it's later today or tomorrow. It might be a little bit of both. And so we'll talk about histamines again. But when cells get injured or infected, they release these histamines, which causes the inflammation. Again, it's all about trying to get those white blood cells to converge on that infected area and start fighting off diseases. So this aspect of this second line of defense of the immune system is what's called cell-mediated immunity, or cell-mediated immune system. So it's where we have certain types of white blood cells, like phagocytes and the T cells, that are attacking and killing the invading cells. So cell-mediated means we have these white blood cells that are attacking our foreign particles, whether it's a parasite or a bacteria or a virus. These cells are attacking it. So that's what makes it the cell-mediated immune system, is that they're living white blood cells that are attacking these invaders. So that's one of the divisions of this second line of immune system defense. Again, these living cells, these cell-mediated immune systems like the phagocytes and the T cells. The other division is called the antibody-mediated immunity, which is controlled by something called antibodies, and it represents sort of the third line of defense in the immune system. So the white blood cells are attacking everything that they can. They're doing their best to recognize these foreign cells, these invading cells. But sometimes they need help. They need extra assistance in recognizing and attacking these cells. And that is where antibodies comes in. And antibodies are a really amazing and cool way that our body recognizes and keeps track of the different diseases that have tried to infect our cells over the course of our lifetime. So antibodies are these sort of Y-shaped cells, or excuse me, they're not cells, they're proteins. And so most infections, so your body is fighting off infections on like a daily or an hourly basis, right? You usually don't really recognize it because most of them don't make it past the first and second levels of defense. So your body's been doing this a long time. It knows how to fight off some of the more common players that are trying to get in. But if something does get in, get past those first two levels and really start to make some issues, that's where these antibodies come into play. So there are these Y-shaped proteins that latch onto foreign particles and basically slow down their movement, cause them to clump together to make it easy to find them, and even do some damage to these foreign particles themselves. So the coolest thing about antibodies is that your body makes, or I should say, your immune system makes thousands of different antibodies because each antibody only binds to one type of binding site, which is known as an antigen. So these two words are really tricky and really easy to mess up because they're both involved with each other in the immune system. Antibodies are the proteins, these Y-shaped things flowing through your blood. Antigens are the little proteins that they bind to, that they connect to. So this is our antibody right here. And then these guys are the antigens, these little kind of protein fragments that the antibody recognizes and binds to. So how does this work in order to keep track of these different disease particles and clump and slow them down? So antibodies are produced by a special type of cell, immune system cell called a B cell. And so essentially what happens is that your white blood cells, your phagocytes, and your T cells break down these invading particles. So here we have our white blood cell attacking some little bacterias. So when they break up these cells, these bacteria have little proteins on the surface of the cell, like little tiny tags that are only 1 or 2 proteins long. So these white blood cells will show these pieces of protein from the virus or from the bacteria to the B cells. And then the B cells will produce antibodies that are specifically designed to recognize and attach to those specific proteins. So each type of invading cell that your body has fought off and broken down, you're now able to produce antibodies that can find and attach to that single type of cell. So over the course of your lifetime, you're going to come into contact with thousands of different foreign invaders, each one having a different set of antigens. And so your immune system develops over time and produces thousands of different types of antibodies, each one that targets and attaches to a specific antigen. So your B cells make your antibodies, and your antibodies identify and attach to the foreign cell. So this is what, over time, gives us immunity to certain diseases. So when you're first come into contact with a new disease, you're going to get pretty sick. Your body has never seen this disease before. It doesn't have the antibodies to recognize this disease right away. And so it's going to take a little while for your body to produce these antibodies that can help attack these cells. You're still going to have your white blood cells attacking and trying to fight off the disease, but it's not until those antibodies are made that you can really start to turn the tide and fight off an infection. So when you start producing antibodies for a specific disease or a specific infection, that means that the next time that you get infected with that material, your antibodies for that material are going to recognize it pretty quickly, start clumping up, start calling attention to the white blood cells early, and depending on what type of disease it is, you might be able to almost immediately fight it off. So by fighting off that disease once and developing antibodies from it, you now may never become ill from that specific invader once again. You now have immunity to those specific cells. So on this chart, we have the amount of antibodies that are made when exposed to a specific antigen to a specific type of foreign cell. So the first time, you may only make a few dozen antibodies while you're trying to fight off that disease, right? So your white blood cells are working overtime. You're slowly producing a small number of antibodies that can now recognize that disease. So you fight off that infection the first time. And if you get infected again, now, because you still have those antibodies from the first go round, you're able to very quickly recognize that disease particle and not just make dozens of copies, but make hundreds and thousands of copies of antibodies to quickly recognize and fight off that disease in hopefully a shorter period of time. Okay, so before we move on, does anybody have any questions, concerns, thoughts about antibodies, antigens, or how they work in order to develop immunity? All right, if not, then we will keep moving on. All right, so speaking of immunity, immunity is when you have a resistance to a specific disease-causing organism or other type of harmful substance. And we can break down the type of immunity that you have to certain pathogens, to certain diseases, to two different types. One that's called active immunity and one that's called passive immunity. So active immunity is basically just exactly what we were talking about. You produce the antibodies for disease. You've been exposed to the disease and its specific antigens in the past, either because you caught the disease, so you got sick, your body made antibodies, you got better, and now you have antibodies for that disease in your body ready to go should it come back. Or you have some sort of planned exposure to a weakened or killed form of the disease of the antigen. So you didn't really get sick, but you were given the disease on purpose, a weak form of the disease. Your body made antibodies for it. And so now, should you ever get exposed to that disease again in a stronger form, you can more easily fight it off.
Flu shot.
Bingo. So specifically, vaccines. So the second type of active immunity is called vaccines. So again, active immunity is where you are producing the antibodies for this disease on your own, either because you contracted the disease, fought it off the first time, and now have antibodies for if it tries to infect you again, or you were purposely given a weak form of the disease and now have antibodies for that disease in your blood, and that is called a vaccine. So when you go to the doctor to get your flu shot, or like I have a 1-year-old, so she's gotten several different types of shots over the course of her life already. And so vaccines are developed where we are deliberately infecting you with a disease-causing pathogen, either a bacteria or a virus or a parasite, in order for your body to start producing antibodies. The twist for the vaccine is that we're injecting you with a killed or extremely weakened version of the bacteria or virus. So it's literally, like, if you want to think about it kind of a morbid way, It's literally like injecting your body with a whole bunch of dead bacteria corpses, then your body looking at those being like, okay, I know what this looks like. I'll recognize it next time. So that if you are infected with that bacteria in its normal version again, your body can immediately ramp up antibody protection and attack that bacteria or that virus. So by giving you the weak version that you were pretty easily able to fight off, you can easily fight off the stronger version should it attempt to infect you again. So vaccines are a game changer in the terms of medical science, and they have allowed us to either nearly or totally eradicate certain diseases such as polio or smallpox from the face of the earth. All right, in the year 2020, nobody on earth should be contracting polio or smallpox. We have essentially eliminated those diseases from the surface of the earth due to a worldwide effort to get almost everybody in the world vaccinated against those diseases. So active immunity can last for different amounts of time depending on the antigen. So depending on what your body recognizes about the disease particle. So some diseases, like the flu, can rapidly mutate into new forms that our body doesn't recognize. So the reason that you have to get a yearly flu shot, and that you should get a yearly flu shot, especially this year, please get your flu shot. These certain types, especially the viruses, can rapidly change and mutate so that they develop new antigens on their surface, meaning that now your body doesn't recognize them. Or some things like the rhinoviruses that cause the common cold, we can't develop an immunity for them because there are hundreds of different rhinoviruses out there. And there's constantly change in which types are the most common in the population. Same thing with the flu. There are tons of different flu strains out there. We just get immunized against the ones that are most likely to be the most dangerous for this year. So in diseases that can change over the course of our lifetime, we might need multiple vaccinations in order to stay as protected as possible. That's also why some shots require you to get a booster shot every 5 to 10 years, is that the antigens of that disease might have changed slightly over the course of that time, or if your body hasn't fought against a particular antigen in a long time, it may not be able to produce the antibodies for that disease as effectively. So the booster shots help to kind of remind our immune system of, oh yeah, that's what that particular disease looks like. I remember now, I got it. Others, such as the chickenpox vaccine, last for a lifetime. Once the chickenpox vaccine is a slow mutating virus, so the antigens don't really change over the course of a person's lifetime, 60, 70 years. So once you get the vaccine once, then you're all set. And it's one that, for whatever reason, your body does a better job of producing antibodies for over the course of your lifetime. So that is active immunity. Immunity that you gain by producing antibodies for a specific disease because that disease got into your body cells at some point, whether on purpose with the vaccine or you caught it in the course of an infection. There's also passive immunity. So this is where it's immunity produced from antibodies that we actually did not start producing ourselves. Instead, they got they're antibodies that got passed on to us from your mom during her pregnancy. So babies, even though they're brand new to the world and hopefully haven't been infected with any diseases yet, they still have immunity against some antigens, against some diseases, because they already have antibodies that they inherited from their mother. So passive immunity doesn't last for your whole lifetime. It lasts until the antibodies that you inherited from your mother die. Antibodies are proteins in cells like any other. They don't last forever. So eventually they'll start breaking down. But hopefully the idea is that by the time your passive immunity antibodies start breaking down, you've already started developing some active immunity antibodies on your own, even as a little baby. So passive immunity, antibodies you get as a baby, inherited from your mom. Active immunity is the one that you have for the rest of your life, where you are producing the antibodies against the diseases that you encounter in your day-to-day life. All right, so a couple either common or important immune disorders that are out there. One of them, especially that you encounter in the Central Texas area, are allergies. So some allergies, like allergies to pollen or mold, can be annoying, but not life-threatening. Other allergies, like allergies to medication or bee venom, bee stings, or peanuts, can be much worse. So allergies are essentially what happens when your immune system overreacts to a relatively harmless foreign particle. So like the pollen that trees release into an air, it is a foreign particle, right? It is a not human particle that can pretty commonly get into your body by breathing. Unfortunately, in a lot of people, their immune system will detect these foreign particles, and instead of saying, oh, it's just pollen, just make sure it doesn't interfere with breathing and we'll be good, and instead will launch a overt immune response. So it says, we've got some nasty stuff coming in. We've got to throw all of our defenses at the book to prevent this from killing our poor human. So that's why a lot of the allergies that float around in the air, like pollen, you inhale them through your nose and your mouth, and they get in a little bit around your eyes, which is why your eyes start watering, your nose starts running, because your immune system is trying to drive out all of those foreign particles. And one of the ways it can do that is by just shoving mucus out the front of your nose. So I mentioned earlier that histamines are what cause the immune system to gang up and attack a certain area. So a lot of the medications for allergies are antihistamines, essentially trying to slow down your immune system in areas where the histamines are being produced, to kind of cut back on some of these rough symptoms that allergy sufferers are going through. So allergies are overreactions to foreign particles. In serious cases, like say when people who have a peanut allergy swallow a peanut, the reason it can be deadly is that the immune system detects peanut particles in the throat, so it'll send all of those histamines and those white blood cells to the area around the throat, which causes inflammation, which can close up the throat and make it hard or impossible to breathe. So that's where allergies go from being annoying to potentially deadly, is our immune response kicks into high drive And even though it's harmful to us, all it is concerned about is dealing with what it perceives as a dangerous foreign invader. All right, and then probably one of the most damaging immune diseases out there is acquired immune deficiency syndrome, also known as AIDS. So AIDS is the disease caused by the human immunodeficiency virus, or HIV. So HIV is the virus particle that it gets in there and infects your cells. AIDS is the disease you get, or the syndrome that you have, due to your immune system cells being compromised. So because the tricky thing about the HIV, about HIV or the HI virus, is that it doesn't just infect any cells in your body. It specifically targets and infects T cells. So we mentioned earlier that T cells are the cells that are responsible for recognizing and destroying infected cells in your body. HIV comes in, specifically attacks and kills those T cells. So now they're not responding to diseases, which means that other normally harmless diseases are able to get past that second line of defense much more easily than they used to be. So we don't get our normal immune response to different types of infections. So our body has a hard time recognizing HIV because the things that are supposed to recognize HIV are the cells getting killed by HIV. So in terms of the damage that viruses do, on a whole body scale, the HIV virus doesn't actually cause that much damage to your body itself, right? If all you had to worry about in the outside world was HIV, it wouldn't really be a big deal. It just targets those T cells, and it's not a particularly aggressive virus. It kind of takes a while to develop. Unfortunately, because the HIV virus does attack those T cells, it cripples your immune system, which means now all sorts of other invaders that normally would be pretty easily held at bay can now cause total havoc on the rest of your body. So normally, pneumonia, a fairly common infection that most people with normal healthy immune systems are able to fight off with minimal help from medicine, can be a major killer of people with AIDS because of the fact that their immune system isn't able to effectively fight off these minor infections. Again, sometimes it can take a long time for HIV to spread far enough where AIDS develops. It could be several months all the way up to 10 years. So somebody could have the HIV virus circulating in their system for 10 years and not really start feeling any of those effects until well into the multiple years after that initial infection. So while HIV and AIDS has spread across the world, luckily today, even though it affects a lot of people, so as of 2007, so over 10 years ago, it had infected approximately 33.2 million people across the globe. Today, obviously, it's much more, but luckily, it is less of a death sentence as it used to be. There's now a lot of antiviral and preventative medication that can help people who do have HIV and AIDS to live much longer lives with limited risk of other infections becoming an issue, as well as there are a lot of medications that help people who do have AIDS and HIV stop spreading it to other people. So one of the few good things about the HIV virus is that it has to travel through direct contact with bodily fluids of one person to another. So if somebody with HIV sneezes on you or coughs on you, that is not going to transmit the virus. It has to be transmitted by sexual contact, so sexual bodily fluids can transmit it. And it can be transmitted by blood, so infected blood transfusions or contaminated needles. So for a while, HIV was a big deal for people in the drug community because they would share their needles that they were using to inject themselves with the drugs with. And if one person had HIV and some of their blood got on that needle, and then the next person injected that needle into their arm, that is direct contact between blood fluids. But again, respiratory fluids like coughing and sneezing or spitting, those do not contain HIV virus particles. Those cannot spread HIV. It has to be through that direct transmission of bodily fluids. Right, and I think that brings us to the end of the notes for today. So we'll go into a little bit more details on a couple different aspects of the immune system on Thursday, specifically more information around fever and inflammation and vaccines and those antibodies and antigens. But does anybody have any final immune system related questions tonight? Alrighty, so I know the immune system is a ton of information that I'm kind of throwing at you right here in the last couple weeks of school. So I wanted to keep the assignments for this week pretty simple and straightforward and really have them focus in on some of the most major and important aspects that I want you guys to know about the immune system. So the assignments for this week is just a series of questions that you can answer for the most part in 1 to 2 sentences. The first one wasn't even about the immune system. It was sort of a review from last week having to do with waste products and how they are separated and filtered from the blood. So a little bit of review of the excretory system last week. And then the assignment tomorrow has to do with the different layers of the immune system. So that first line of defense and what all is involved in there. And then the Thursday's question has to do with these white blood cells and specifically with HIV and how HIV affects the immune system. So like I said, we'll go into a little bit more detail on some of this immune system and the different immune responses we have to infection during the Zoom class tomorrow evening.